Hello, welcome back. My name is Dem, and I'm a third-year CS major here at Tech, and I'm a full-stack developer for this project.
I'm Jackson O'Connell. I'm a fourth year business and CS student at Tech, and I'm a backend developer for this project.
Hi, I'm Mai Trey. I'm a second year CS student at Georgia Tech, and I'm the Scrum Master for this project.
My name is Nathaniel. I'm a second year CS major and I'm the front-end developer.
And welcome to our Chapter 2 of the CS 2340 podcast. In this chapter, we'll dig into code quality, code smells, refactoring, and test-driven development. We'll show real examples from our MyApply Django app, where the code got messy, how we would clean it up, and how we could have prevented complexity using TDD. We're going to walk through 3 parts. Number 1, code smells we found in our repo. Number 2, refactoring stories and how we'd fix them. And number 3, for TDD, how tests could drive clean architecture.
So what is a code smell? A code smell is a visible symptom that sometimes is off in the design, but it's not necessarily a bug in the code. But like the app can work fine, but smells suggest technical debt, maintainability risks, or unclear responsibilities. Identifying smells early lets you refactor before the problems scale and the issue gets much larger.
And these are super common in rapid development, especially in AI backend features that start as prototypes and then grow into full features. The plan is to meticulously delineate a set of 5 distinct software code or design smells. For each of these identified smells, a comprehensive breakdown will be provided, encompassing the following 4 crucial components. Number 1, the definition and rationale, also known as the what and why. A detailed explanation of what the smell constitutes, along with the underlying reasons for its existence and why it is considered problematic within the context of software quality. Number 2, location and manifestation, where it is. A clear description of the typical places within the codebase or design structure where this particular smell tends to manifest itself and be observed. Number 3, impact and detriment, also known as how it hurts. An analysis of the negative consequences and detrimental effects that the presence of this smell has on the maintainability, readability, performance, or overall robustness of the software system. And lastly, preliminary remediation strategies, or simple fix ideas. A presentation of several initial straightforward concepts and suggestions for mitigating, refactoring, or otherwise resolving the identified smell.
So now we'll go back to the services Python file and the systems tailoring app, specifically looking at the class agent kit tailoring service. And as you can see, if you scroll through the class, it is a very, very massive monolith of a class. And so this is probably one of the most significant architectural flaws we've identified, or a pervasive code smell, is this unmistakable presence of a kind of like God class design anti-pattern. So this is most acutely manifested in that agent kit tailoring service class, which has meta size to an unmanageable size, currently exceeding, I think, over 1,700 lines of code. So this single monolithic class has been improperly burdened with a vastly excessive scope of responsibilities, effectively handling almost every aspect of the agent's core functionality, which includes, but is not limited to, external API communications, including managing all interface calls to external services such as the OpenAI platform, the data structure interpretation, implementing the necessary logic for complex job parsing in a JSON format, relevance quantification, which is executing intricate algorithms for snippet scoring to determine relevance to a job description, which would dictate if certain parts of a user's experience graph are included in that final output or used to generate it. And then integrity enforcement, which is applying and managing system-wide guardrails to ensure compliant operation. Document synthesis, performing the complete process of resume generation via a separate API call. And then compatibility assessment, which is calculating the metrics for the applicant tracking system to see which keywords are met and which ones are missing. And then resource monitoring, tracking, and then optimizing the token usage per user for cost control. So what we don't want to do, for example, is to load the user's entire experience graph into an OpenAI API call, because that would just use an exorbitant amount of tokens. So instead, we can kind of search before including parts of the experience graph in that call. And then there's ancillary document creation, which is producing supplementary materials like the cover letters, which is optional. And then resilience management, which is implementing comprehensive error handling and recovery mechanisms, such as providing the user with a debug log. So in its current state, this class is in direct and severe violation of the fundamental object-oriented design principle, known as the single responsibility principle, or SRP, which dictates that a class should only have one reason to change. The agent kit tailoring service, by contrast, has many disparate reasons to be modified, leading to an inherently fragile, complex, and difficult to maintain code base.
Jackson, how would you say that this problem became worse throughout our 2 sprints?
In hindsight, I think it started as a small experiment for resume generation. And then as we continued to add new user stories, beef out the features, and then especially near the end, as we became more focused on the token optimization for users, this single monolithic class kind of became the hub, because it was already working and it made sense to just add it to that existing class. But in the end, every new idea got bolted into the same class, which violated that principle.
This also has further front-end consequences. Any future UI features, like supporting different resume formats, would require modifying this giant file instead of extending clean interfaces.
So to fix it, we would extract several distinct single-purpose components to adhere to that single responsibility principle and create a more maintainable architecture. So we went ahead and reviewed that monolithic class and identified 5 different singular responsibilities that we can segment it out to. So the first would be like job profile builder. This component would be responsible for parsing the job description and extracting key skills, required experience, and necessary qualifications to construct a detailed machine job profile. Then there would be snippet selector. Its sole job would be to analyze the user's resume content against the profile generated by the job profile builder and select the most relevant targeted snippets and bullet points from the resume. Next would be the OpenAI resume client. This client would manage the system's API calls to the large language models, specifically OpenAI's API. And we've been using, I think, the 4.0 model, 4.0 mini, to conserve tokens. It would securely handle the API key, format the prompt using the selected resume snippets and the job profile, and manage the communication for generating the initial draft of the cover letter. Finally, the penultimate one would be the guardrail validator. So before the final output is presented, this crucial component would enforce quality and compliance checks, ensuring that the answer or output is grounded in the user's experience graph. It would validate the generated cover letter and any other supplemental materials against predefined rules, checking for tone, length, absence of hallucinations, and ensuring it directly addresses the job requirements. And then finally, we identified that it would make sense to make a cover letter generator separately. So this is a supplemental material, not part of the resume, but we think it would probably be used enough to dictate and justify making it a separate method. So the cover letter generator would act as the facade, which we talked about in chapter 1, orchestrating the calls to these separate dedicated components in a clean sequential manner. This design significantly reduces coupling between modules and makes isolated unit testing for each piece of functionality much simpler and more reliable.
So that architectural shift, as Jackson just talked about, wouldn't just clean up the code base, it would fundamentally change how we work in sprints. Right now, every new feature feels like a gamble because we're editing the same 1,700 line God class. One mistake can ripple across the entire pipeline. If we just break this down into small single purpose classes, sorry, I just lost my place in the script. If we break this down into single purpose classes, new functionality becomes safe, modular tasks instead of change 1,800 lines of code. The backlog items become implement aggressive strategy or like add a guardrail validated rule.
Very good.
So inside the God class, the generate resume package is about 300 lines. So this is a long method smell, another code smell that we've identified. It builds prompts, calls the OpenAI API, parses responses, applies guardrails, and optionally generates cover letters and more. So it's a whole pipeline in one singular method.
And why would you say that all of that is risky?
Well, the current monolithic approach to testing is inherently problematic. The fundamental flaw lies in the deeply interconnected nature of the components, making true unit testing an impossibility. Specifically, you simply cannot test each piece of the system in isolation and expect meaningful results in the current setup. A seemingly minor modification, such as the change in the prompt's formatting at the beginning or the end of the processing pipeline, can have cascading and unpredictable consequences that could entirely break the parsing logic situated hundreds of lines downstream in the code. This tight coupling means that fixing one area often introduces regressions in another, leading to a brittle and very unstable code base. Furthermore, this intertwined complexity severely impacts the code review process. When everything is bundled together, reviewers are forced to scroll endlessly through massive files, trying to trace the flow of logic and identify potential edge cases. This makes thorough and efficient code review extremely painful and time consuming, significantly increasing the likelihood that subtle but critical bugs will be missed, ultimately hindering our ability to maintain quality and agility for our system during development.
And once again, if we added multiple resume formats, then this would turn into ugly nested branching everywhere and make the readability even worse.
So the way we've identified to fix this is just the application of the extract method, refactoring technique, which would be central to improving the design of the system, specifically by breaking down a potentially monolithic function like this one into a set of highly focused single responsibility helper methods. For instance, a primary complex function responsible for end-to-end process of generating a personalized document, such as a cover letter specifically, would be decomposed into the following more specific manageable components. So a few four specifically that we've identified would be first to build prompt. This method would be solely responsible for gathering all necessary input variables. This could be the recipient's name, job title, company details, or the sender's qualifications, and then structuring those details into a single coherent, well-formatted string or object that adheres to the large language model's required input specification for either the system or user instructions. Then another individual component we could use is parse output. So after the LLM processes the prompt, the raw text output often contains artifacts surrounding explanatory text or specific structural elements that need to be cleaned up. This method would handle the parsing, validation, and serialization of the raw LLM response into a usable structured data format, ensuring only the core content is retained. Next, apply guardrails. This would be a critical safety and quality control layer. This method would enforce necessary business logic, compliance rules, and ethical guidelines. It could check for inappropriate language, identify and filter out hallucinations, and ensure the generated content adheres to a specific length or tone as set by the user, and confirm that all necessary fields like contact information are present. And then lastly, we could have generate cover letter. This represents the final orchestrating step. It would combine the process and validated content produced from the previous methods into the final document structure, handling formatting, template application, and potentially outputting the result to a file, email, database, or another output of an IO. Even with a formal strategy design pattern where different algorithms for the same overall goal are interchangeable at runtime, this modular approach significantly reduces the cognitive load on developers during code smells and debugging and fixing. Each small method is easier to read, test, debug, and maintain because its purpose is narrowly defined. A developer troubleshooting the LLM's response format, for example, knows immediately to focus on parse output rather than sifting through hundreds of lines of a long master monolithic function. And this, again, adheres to the single responsibility principle and would be a major win for the code quality for the system. So now we'll look at the views, tasks, and front-end views Python files all in the tailoring application. So we track token usage in 3 different places: token tracker, usage aggregator, and billing service. In each of these files, we have essentially copied and pasted the same block of logic to calculate and record token consumption for user sessions. This identical repeated code is a classic example of duplicated code smell, which is a significant issue in software maintainability. The primary drawback is the substantial overhead for these modifications. For example, if the product team decides to change the token usage calculation methodology, such as moving for a simple token count to a more sophisticated calculation that counts words or characters, or maybe relies on the compute time, or maybe applying a weighted factor for different models. For example, newer models would consume more tokens, similar to how some coding agents work. And we are forced to locate and edit all 3 of those files in the current setup. So this process is time consuming, highly prone to error, and dramatically increases the risk of introducing inconsistencies in our product. And a failure to update the logic identically in even one of the 3 locations will result in skewed data, incorrect billing, or misleading usage reports, leading to financial and data integrity problems. So to resolve this, the common calculation logic should be extracted and consolidated into a single well-tested function or class within a dedicated utility module. The 3 disparate services would then call the central module, ensuring a single source of truth for the token usage calculation. This refactoring would eliminate the duplication, simplify future maintenance, and make the code base more robust and easier to understand.
That's also known as a shotgun surgery risk, where one conceptual change causes many edits.
And for UX, inconsistent tracking could break photo logic on some endpoints and not others.
So one way we can fix this is to just pull this logic into a helper function. For example, in account utilities.python, something like record token usage with session and user as parameters. We could have a single callable function, and in each place where token usage needs to be tracked or used to reduce a user's tokens, we can just rely on this single centralized record token usage helper function. So another code smell we identified is feature envy. So if we go to the models.py file and the job apps, and we get to the get tailoring stats method, here you can see that method reaches into the tailoring session internals, summing the token usage across sessions. And that's what we call feature envy. The logic belongs with tailoring session, not job posting.
So the model is reaching into another model's details.
This is also a really big data risk for data integrity and schema dependency. The current system design exhibits a tight coupling between the tailoring session component and the job posting component. Specifically, job posting relies on the schema or structure of data provided by tailoring session. This has an impact as a modification to the internal structure or schema of tailoring session such as renaming a field, changing a data type, or removing a required attribute, to lead to a silent failure within job posting. This failure would be silent because the compilation or basic execution might proceed without immediate error, but the logic within job posting would break due to receiving malformed or unexpected data. This could result in incorrect data processing, failed job matching, or system instability without immediate explicit error notifications. This is a high severity, as silent failures are difficult to detect and debug, potentially leading to corrupted data or a poor user experience. A few potential mitigation strategies for this include introducing a data transfer object, DTO, or an interface. Decouple the two components by having a tailoring session to communicate its data via a stable, versioned interface or a dedicated DTO. Job posting would depend only on this contract, not the internal schema of tailoring session. So as tailoring session is updated, job posting won't need to will get the same data as expected. Another method would be schema validation and versioning, implementing robust runtime validation within job posting to check the received data structure against an expected schema. If a mismatch is detected, an explicit logged error should be raised. Additionally, versioning the API or data structure will help manage change incrementally. End-to-end testing is our final stage, ensuring that integration tests specifically cover the data flow between tailoring session and job posting to catch schema discrepancies early in the development cycle.
So a simple way we could fix this is moving the aggregation logic into the tailoring session or a dedicated stat service, which is kind of similar to what we talked about previously with having a centralized token utilization calculator that all external methods call. And that way we rely on the same data and same methodology for calculating that. So another code smell we have is primitive obsession and magic numbers. So if we go to the services Python file in the tailoring app, we can scroll to the part that focuses on the experience graph parsing. So the experience graph is that just like mega resume of all professional, academic, and personal projects that a user has recorded. And we pass experience graphs around as raw dictionaries and constantly check keys like title, company, etc. And that's a primitive obsession because there's no strong model representing experience entries. And we also have kind of arbitrary magic numbers for token limits, such as 3,500, 6,500, etc., which equates to some number of words, but is kind of set randomly and doesn't take into consideration that some sections might be important, but take a lot of words.
What would make this clearer?
So something that would make this experience graph parsing cleaner would be maybe like a domain model, like experience entry plus constants like max tokens per bullet. That removes the scattered raw values.
Next, let's do a quick before and after on the God class.
So this refactoring story, this first refactoring story, it's focused on the agent kit tailoring service, which, as we said, was a monolithic class, and it had basically everything. So if we can scroll to that class, you can just see how massive it is. And all the methods live here, from parsing jobs to generating bullets to recording usage. And that was before the refactor. So then after refactoring, we split that monolithic call or class and methods into 4 core components. So first is that job profile builder, analyzes the job description to extract and structure requirements, keywords, and qualifications. The snippet selector, comparing extracted requirements against the candidate's full experience, ranking, selecting the most relevant snippets, project descriptions, and skills to address the job needs. A resume generator, which synthesizes the structured requirements and ranked snippets to build a prompt, which is sent to the OpenAI API LLM to generate the final tailored resume for the cover letter. And then guardrail validator, which acts as a quality assurance layer, reviewing the LLM's output for factual accuracy, professional tone, and compliance with ethical and formatting standards before presenting it to the user. And this is that facade of the AgentKit tailoring service. The entire process is managed and simplified with a high-level service object, the AgentKit tailoring service. This object operates as a facade, providing a unified, clean interface to the client. Its role is purely one of coordination and workflow management. It orchestrates the sequence of calls between the job profile builder, snippet selector, resume generator, and guardrail validator, abstracting the complexity of the underlying system from the external users.
So this allows us to modularize the experience. The UI can add new tailoring modes without having to touch these massive files.
And this aligns with our patterns from chapter 1, which was about facade, template, method, govern, and strategy. This refactoring isn't just about breaking a big class into small ones. It's about embedding proven design patterns into the architecture. Each extracted component has a single responsibility, and the orchestration is handled in a structured, pattern-driven way. That means future changes won't require risky edits to a monolith. Instead, there'll be isolated additions or like substitutions. The result is a code base that's easier to extend, safer to modify, and more resilient to change. In short, refactoring into smaller classes transforms risky edits into predictable bite-sized stories. It reduces the cognitive load and increases the confidence in deployments and accelerates delivery. This is how we move from firefighting to like a fragile system to iterating quickly in a resilient architecture.
And moving on now to our second story, duplicated token logic.
So one example of duplicated token logic is in the tasks Python file in the tailoring app where usage is recorded. The fundamental concept revolves around implementing the don't repeat yourself or DRY software engineering principle, specifically for the mechanism responsible for monitoring token utilization, which we were talking about earlier, and subsequently adjusting user quotas. Rather than having the token usage recording process, which consists of incrementing the user's token count with the result tokens, represented by user.tokensUsed, added with the results.tokens, immediately followed by persisting the change via user.save, committing that adjustment. And that's duplicated throughout the application in what could be around 3 distinct files or functional blocks, and the shared procedural behavior is consolidated. It is instead isolated and encapsulated within a single dedicated centralized helper function named record usage with parameters user and result. Through this process of centralizing the logic, any subsequent modifications or enhancements to the methodology by which user quotas are computed, stored, or managed are strictly limited to this solitary helper function. This approach significantly streamlines the maintenance overhead and crucially guarantees uniformity and dependability in quota management across the entirety of the codebase. As a direct result, the probability of inadvertently introducing defects or inconsistencies when revising business logic pertaining to user quotas is substantially diminished. Code reusability is maintained.
And this makes sprint work smaller. The tasks are like broken down and they're and new reporting metrics only need one change. Next, we're moving on to TDD, which stands for test-driven development. So TDD workflow is broken down into red, green, and refactor. So basically the first step is write a failing test for write a failing test for the behavior you want. And the second step is to implement a minimum code base, a code to pass, and then clean up the implementation while tests keep it safe. So the definition is to basically write a test before the class is tested. The developer writes unit testing code for nearly all production code. Then they write a test code that fulfills the requirements, and they write functional code that's the working code that fulfills the requirements, and then they refactor, which is cleaning up the work code that fulfills the requirements.
Our code was built iteratively, but not with strict TDD. We have tests, but most are integration or patch-based, not true DDD cycles.
So if we go to the test services Python file, you can kind of see the normalized parameters test, which is at the top of the file. This test perfectly aligns with the test-driven deployment principles by verifying pure isolated behavior. It avoids external dependencies like APIs or databases and focuses on straightforward input, process, output, specifically ensuring correctly normalized values. This clear isolated function is an excellent test-driven deployment target, allowing easy red-green refactor. The test is fast, deterministic, and guards the core normalization logic against regressions.
As a front-end dev, this matters because back-end uncertainty can translate into UI bugs. TDD helps stabilize predictable behavior.
Let's show what a full TDD cycle might look like.
So let's take the function check and increment tokens in the accounts utils.py file. This function is responsible for managing a user's request token quota before allowing an action to proceed. So what's the expected behavior? First, we would want to check quota. The function first checks the user's available token quota, and then we'd want to allow the request. So if the user has sufficient token quota remaining, the function should allow the request to proceed. Crucially, it must also increment the use token count for the user before returning a success status. And then we should also have some functionality to block a request. So if the user does not have any quota left, like if the quota is 0 or the available tokens left are 0, the function must block the request to return a failure status without incrementing the token count. So we don't want to charge users for tokens they didn't spend, but we don't also want to spend them even if we don't provide the user with the output. So we can look at a certain method definition. So let's say test block when exceeding quota, and where user will equal the user with parameter of a token quota like 100 and the token used like 98, therefore with 2 tokens to spare. And then with a PyTest raise error, so like PyTest.raises quota exceeded, we can check and increment tokens with parameters like the user and then the number of requested tokens. So that would be basically the red part of the test deployment. And then we would want to implement the quota check and then raise the number. And then when refactoring, we would improve the error type, log the usage, and then tighten the unit tests to be most aligned with the end system.
So TDD is used to basically make sure your code is correct and works properly when you're implementing code or when you're writing code, so that you can push changes confidently and make sure that your system doesn't break under unforeseen checks or certain test cases.
A second example would be ATS scoring.
So ATS scoring is pretty important. So we can do this with the function calculate ATS score in the resume optimizer file. So what this would look like would be defining the test perfect match scores high. So we're trying to find high matches for the ATS to use keywords that are most impactful and then make sure they're actually in the outputted resume bullets or cover letter. So some parameters we'd set would be like job with a dictionary with like skills as a key, maybe Python as one of the values in for that key. It could be like a list though, in case there's multiple skills, like if you needed multiple programming languages listed. And then you would pass that to the resume, and then the score would call that calculate ATS score by first looking at the job, where the ATS parameters, you could say, would be kept in the dictionary, and then you're going to compare it to the resume, which is also a dictionary with the parameters. And then what that method will do is really just compare it. And so then you can just set a cert score to be like greater than 80. So that's what you want the score to be. So for the green part of this, the assignment requires implementing simple matching logic, so a basic algorithm to compare 2 data points against predefined criteria to determine a match for the ATS specifically. So some essential implementation points for this would be first defining what is simple, focusing on the straightforward direct attribute to attribute comparison. For example, everything on a job description might not perfectly match with everything on a resume, but certain things like programming languages like Python would probably be pretty consistent across certain types of roles. So then we want to look at input structure. So clearly defining the data format, maybe like objects with ID, name, and value. And then matching criteria. This would be establishing the precise conditions such as exact match, partial match, tolerance. Maybe it could be something as simple as Python uppercase with Python lowercase, or maybe understanding that if you know Java, you might be comfortable with other object-oriented programming languages as well. And then also attribute combination, requiring matches across multiple non-key fields. So the fourth implementation point would be the actual implementation of this, which would encapsulate the logic in a dedicated function, like maybe a Boolean is match. That way you can see true or false if it's a valid match. And then also the efficiency, ensuring reasonable performance even with large data sets. So the goal is to create a robust, testable, and clear mechanism for pairing or linking data based on fundamental comparison rules. So to refactor, the next development phase requires incorporating advanced features, such as a weighting system for prioritizing components and a missing critical list to flag essential unmet requirements. Crucially, as these features are implemented, the system must continue to pass the established passing test to ensure backward compatibility and prevent regressions. This demands an iterative, validated architectural design.
So to round up, in one sentence each, why do code quality and TDD matter for this project?
To keep it simple, we're calling complex AI services. So controlled code boundaries prevent silent failures.
UX also relies on predictable backend behavior. Refactoring and TDD reduce strange or unpredictable edge cases.
TDD makes iteration safer. When adding to a new feature, tests fail. Tests tell you if they broke something in the code.
I think that code smells show where the structure could scale. Refactoring stories show that the path forward. And to close off, that wraps up chapter 2. We have covered code smells we found in our Django project, how we'd refactor them, and how TDD could help us scale the system safely. Thank you for listening.
That was much better on time than the other one.
Was that an hour or like 53 minutes?
Not. That was 30,
40
40 minutes.
Oh.
Okay, good.
Okay, well, I'm gonna